Welcome back to the PIAB podcast. We've built a pretty solid foundation, I think, in the last episode.
We have. And if you haven't heard that one, it's probably worth circling back because it sets the stage for what we're talking about today.
Absolutely, because today we are opening up the engine room.
We really are.
Mm-hmm.
And, I take a lot of pride in discussing COAX. It isn't just another component. It's a technological statement for PIAB.
A defining innovation, you'd say.
Absolutely.
Yeah.
It's core to who we are in the automation space. It really sets us apart.
So that's our mission for you today, to pull out the most important bits about COAX development, how it works, and I think most importantly, how you choose the right one for your machine.
Right. It's all about understanding efficiency through what I'd call a very elegant design.
It feels like it.
COAX was really the next generation in vacuum tech. It took that traditional multi-stage concept and just maximized everything, the adaptability, the compact size.
And the name itself, COAX, is a perfect descriptor, isn't it?
It is. It comes from the way all the components are arranged coaxially.
Just wrapped tightly around the nozzle's axis.
Exactly. And that's the secret. That structure is how we can pack so much performance into such a tiny footprint.
It's a philosophy that was proven pretty early on, right? The P3010 was the first big product in the line.
Yeah, that used the mini coax cartridges, and its success really just paved the way for the micro and the midi sizes that we have now.
Okay, let's get into those core mechanics then. We know COAX is a compact, multi-staged ejector technology.
Right, and it's famous because PIAB managed to eliminate those internal flow restrictions and what engineers call dead volumes.
Getting rid of that internal turbulence, that has to be a huge step for efficiency.
It's massive. And here's the really cool part. When compressed air enters the system, let's say at around 3.1 bar or 45 psi, the geometry of that first nozzle is so precise. The air velocity actually surpasses supersonic speed.
Wow, supersonic air. So you're literally shaping the vacuum with that incredible speed.
Yeah.
How does the multi-stage principle then use that?
It's a progressive system, a layered approach. The smallest nozzle, the first one, its whole job is to get to the lowest pressure.
Meaning the deepest vacuum levels.
Exactly. Then the next nozzles are progressively larger. Now, they generate less vacuum pressure on their own, but they provide a much, much higher flow capacity.
So you're using the smallest one for depth and the bigger ones for volume and speed.
You've got it. And the combination of that induced vacuum flow and the now lower pressure compressed air, it all just exhausts safely back at the atmosphere.
Which brings us right to the genius of the energy-saving mode, the flap valves.
The flap valves. So these valves inside the system, they shut sequentially as the vacuum level goes deeper. The valve on the biggest nozzle shuts first once it hits its maximum vacuum.
I saw a diagram of that, and it's a really eye-opening process. But let's focus on that first nozzle, the one doing the deep vacuum work. Why is its valve so important for saving energy?
Well, because traditionally that first stage often doesn't have a valve.
And if there's no valve?
The second you shut off the compressed air to save energy, atmospheric air just rushes right back in through the exhaust.
And collapses the vacuum. You lose your grip instantly.
Instantly. So the key to energy saving is basically a one-way air trap. It's an optional non-return valve.
And it stops the outside air from getting back in?
Precisely. It lets the system maintain the vacuum level. And that's the absolute foundation of the energy-saving mode.
That is just such smart engineering. You secure the vacuum so you don't have to keep burning compressed air just to hold apart.
Okay, so now we get how it works. The next challenge is choosing the right one. And for the traditional product line, there are three main variables to think about.
Size, number of stages, and characteristics.
Let's start with size. You've got micro, mini, and midi. This is all about your capacity.
Simple enough. A larger size generates a greater vacuum flow.
Exactly.
Here's the aha moment for me, and I think it's crucial for anyone designing a system. The physical size of the cartridge. It does not affect the maximum vacuum level it can reach.
That is correct. That's a huge point. The maximum depth is all about the geometry of that first nozzle, not the shell around it.
Okay, so next up is the number of stages. You have 2-stage versus 3-stage.
Right. And this decision really comes down to a balance between physical space and pure speed.
So, what is the actual performance trade-off? If I go with the smaller 2-stage, what am I really losing?
You're losing the sprint at the very beginning. The 3-stage cartridge incorporates an extra, larger nozzle specifically designed to generate massive initial flow.
So, it's about how fast you can evacuate the cup and get that initial grip.
Right. Exactly. It speeds up the pull-down time. But here's the nuance. That extra large nozzle is really only effective at low vacuum. Once the vacuum gets down to a certain level, about 10 negative kPa or 3 inches of mercury is the benchmark. The flow from a 2-stage and a 3-stage becomes roughly the same.
Hold on, let's pause on that benchmark. When you say 3 inches of mercury or 10 negative kPa, what does that mean in practical terms for someone listening?
That's a great question. It means we're past the point where that initial surge of air is critical. It's about 100 millibars. The material is gripped securely.
Got it. So the system is shifting from pulling down to just maintaining or deepening the vacuum.
You've got it. So that third stage really only matters for that critical first fraction of a second.
So then why would a designer ever pay for the 3-stage version if speed isn't the absolute #1 priority? It sounds a bit redundant for a lot of applications.
I mean, that's a fair challenge. For most general applications, you're right. The 2-stage is a fantastic, cost-effective choice. It saves space, too. But for true high-speed applications, like rapid pick-and-place, where every millisecond counts for throughput, that initial flow boost from the 3-stage is non-negotiable.
Ah, so it becomes about reliability.
Total reliability. You guarantee the grip is secured faster, minimizing any risk of dropping apart. You choose 3-stage for speed and performance assurance. You choose 2-stage for cost and a smaller footprint.
That makes the trade-off crystal clear. Okay, before we get into the characteristics, we need the decoder ring, the naming convention. If I see SI32-2, what does that tell me?
That's the full map. The first letters SI, PI, or XI, that's the characteristic, the performance profile.
Okay.
The numbers that follow, like the 32, that's the size of the first nozzle. It gives you a rough idea of capacity.
And the number after the dash, the 2.
That's the number of stages we were just talking about.
Perfect. So let's get into those characteristics, because this is where it really gets specific to the application. We have SI, XI, and PI. Let's start with SI.
SI is your high flow champion. It's engineered for the largest vacuum flow in relation to its energy use. It has the highest flow curves of them all.
And where would you use that?
We recommend it for handling porous materials like cardboard or foam, or anytime you expect surface leakage. The SI just powers through that leakage to keep the vacuum stable. It likes a high feed pressure, around 6 bar or 87 psi.
So SI is the power flow cartridge.
Yeah.
Got it. What about XI? Is that the depth specialist?
XI is all about deep vacuum. It gets to very deep vacuum levels from surprisingly low air consumption. It still has high flow, but its real talent is hitting depth while being efficient with air.
And the pressure for that one?
It prefers more moderate feed pressures, maybe 5 bar, which is equivalent to 72.5 psi, or 4.5 bar, which is equivalent to 65 psi. It depends on the size. You'd use it for sealed surfaces like big smooth panels or glass where you need to maximize holding force.
Which brings us to PI. Now, looking at a flow chart, PI can look like the weakest one. It often has the lowest overall flow, but that's not the whole story, is it?
Not at all. PI is your insurance policy. It's the best way to think of it. It's optimized for reliability when you have fluctuating or low compressed air.
So if the air supply in your factory dips when another big machine kicks on.
Exactly. The PI is designed to achieve a deep vacuum consistently, even at a really low feed pressure of around 3.1 bar or 45 psi.
So you're trading that top-end speed or flow for guaranteed consistency.
Which is often the smarter industrial choice.
Right.
You choose PI not for its peak performance, but because it can operate reliably at a pressure that's lower than the lowest dip you might see in your plant. It's about stability.
That's a critical insight for managing risk. Okay, before we move to the next generation, there are a few specialty cartridges we should touch on. Let's start with the micro line.
Right, the micro are the smallest, and because of that, they do have some limitations. They're only available as 2-stage.
And no internal non-return valve, I read.
Correct. Internally, there just isn't room. So if you need energy saving with the micro cartridge,
you need an external solution.
You do. In products like the Pi Compact 10X, for example, that function is handled by a Pi chip, which has an external non-return valve built in.
Okay, now what about the DI12-2 cartridge? This one's fascinating. It's a 2-stage mini with no flat valves at all. Why on earth would you get rid of the valves?
For dirty environments. This is a huge benefit in certain industries. By taking out the flat valves, the DI becomes incredibly tolerant of dirt, dust, and particles.
Like woodworking or places with a lot of cardboard dust.
Exactly. The DI design pretty much eliminates clogging and all the maintenance downtime that comes with it. It's rugged.
A low-maintenance engine built for uptime. And what about the mini filter silencer, the FS configuration?
Yes, the one used in the P3010 family. That's only a 3-stage. And it basically integrates a nylon filter screen and a silencer right into the red holder part. It's an all-in-one solution for a cleaner, quieter operation.
Which brings us to a major evolution. Around 2015, PIAB introduced the SX COAX cartridges SX12 and SX42.
Right, featured in products like the Pi Compact 23. This is the second generation, and it really changed the game for integration.
How so? What was the big departure in design?
The SX family was developed specifically to be used with a Pi chip 23 housing, and the critical difference is that the SX cartridges themselves have no internal flap valve.
Like the DI, but for a different reason.
For a totally different reason. They rely completely on the Pi chip housing to provide the flap valves externally.
And what's the benefit of separating them like that?
The benefits are huge. It's less sensitive to dust. Service is way easier because you don't have internal alignment issues, and you get a smaller footprint since they're inherently 2-stage.
And the performance.
The SX offers one generic characteristic. It essentially combines the high flow of an SI with the deeper vacuum of an XI into a single, really reliable unit.
It's a move toward being simpler and more robust. And it highlights how COAX cartridges are really just self-contained vacuum engines.
They are. And that allows PIAB to integrate them into so many different product bodies, from a simple Pi line all the way up to a complex Pi Compact system.
And that standalone nature, that must be why they're so valuable for OEMs, for original equipment manufacturers.
That's the ultimate flexibility. It allows the customer to integrate our engine into a body of their own design.
Giving them total control over the shape and fit for their specific machine.
Totally. You can keep the vacuum source as close as possible to the point of use without adding weight or bulk. We see customers doing amazing things with it, like 3D printing custom tools.
Oh, wow.
Yeah, creating zoned vacuum end effectors, like a foam pad with multiple coax cartridges inside, letting them handle complex parts. Customizing the body around the engine is, I think, the ultimate expression of coax.
What an incredible tour. From supersonic air and flat valves to the clear criteria for selection, size, stages, and characteristic. We've learned why SI is for porous materials, XI for deep vacuum efficiency, and PI is that critical insurance policy.
And we saw how that second generation, the SX cartridges, moved the valves externally to make everything more robust and easier to service.
And we spent a lot of time on those subtle but really vital performance trade-offs. The whole reason SI, PI, and XI even exist as separate options.
Right. It's because different applications prioritize different things, flow or depth or just pure stability.
Yeah. And having those specialized options is exactly what ensures you don't have to compromise on performance. You just have to pick the right one.
Exactly. It ensures you get the perfect match for your specific application.
That is a great note to leave it on. Thank you so much for joining us for this deep dive into coax technology.
See you on the next one.